Hi, welcome all to the online classes. I am Mukesh Bhardwaj. Today going to deliver a topic photoelectric effect in engineering physics, BTech first year. Photoelectric effect. So the topic begins with in a metal, the flow of electron or flow of electric current is due to the flow of charged particles called electrons. The electrons are relatively free to move throughout the metal. Electron, gas, or steam. So most metals are good conductors of electricity. By shining light on a metal, some of these electrons can be knocked out of the metal to generate an electric current outside of the metal. Although basic photoelectric effect can be explained with classical wave model of light, then the detailed results of such an experiment can note. Electrical current arises from the flow of charged particle, usually electrons. In the Druid model of a metal, there are many free electrons in which behave like an ideal gas of charged particles. Because of this large number of free charged particles, metals are usually very good electrical conductors. If electrons in a metal behave as an ideal gas, we expect them to have a spread of kinetic energies. Maxwell Boltzmann velocity distribution, the probability that a molecule has a speed between v plus and v plus dv is the fv dv, where fv is equals to m by 2 pi kt whole to the power 3 by 2 into 4 pi v square e to the power minus mv square by kt. So in 1887, while experimenting on electromagnetic waves, Hertz observed that electric discharge between electrodes of discharge tube become easier when ultraviolet rays were incident on the cathode negative plate. Hallwatch in 1888 verified it and concluded that the number of charged particles in the discharge tube increased due to the ultraviolet rays. In 1898, J.J. Thomson and in 900, Lenard proved by their experiment that electrons are emitted when light of certain wavelength is incident on metal plates. This phenomenon of emission of electrons from metal plates due to light of suitable wavelength incident on them is called photoelectric effect. So suitable wavelength of light when strike on a material, some kind of material, then a emission of electrons takes place, and this is called the photoelectric effect. The electrons who emitted are called photoelectrons. The current produced due to the flow of photoelectrons is termed as photoelectric current. The metals which emit electrons by photoelectric effect are called photoelectron emitters. All metals can be used as electron emitters, but their emission efficiencies are different. Due to the high efficiency of alkali metals as electron emitters, they are used as photosensitive materials. Next. Electrons do not normally spontaneously leak out of the metal. There must be something that keeps them in place. There's something that keeps them in place. A swimming pool analogy: suppose if water is there in a wall and the level of water is shown in this, water is confined by the region of increased gravitational potential line, that is the wall. Electron gas, electrons are confined by the region of increased electrostatic potential, that is the metal surface. The extra energy required to remove the most energetic electrons from the metal is called the work function of phi of the metal. This is the arrangement of the photoelectric effect, or we can say that how the detection of an emitted electrons can be analyzed. We just take the vacuum chamber in which two electrodes are connected. After that, energy in, electrons are start moving, current start flowing, current flow. Monochromatic light in, variable voltage, the photoelectric effect. This is the pictorial representation of a photoelectric effect tube, or we can say that experimental arrangement. Metallic anode and cathode enclosed in a vacuated glass tube like old-fashioned electronic valve. Vacuum required so that electrons can flow from cathode to anode without scattering from gas molecules. Monochromatic light is shown on the cathode. Electrons flow from cathode to anode, current detected by galvanometer. Potential divider to vary anode cathode voltage. Okay. Now the pink lines, electric field lines, because electrons are negatively charged, they move in the opposite direction to the field lines. When the cathode is illuminated with the light of frequency above a certain threshold frequency, current is detected. That is, photoelectrons must be ejected from the metal. When the cathode is illuminated with the light of frequency above certain threshold and frequency, current is detected. That is, photoelectrons must be ejected from the metal. Electrons emitted instantaneously, even for the lowest intensity of light. If the frequency of the incident light is below the threshold frequency, no electrons emitted, no matter how intense the light is. If the light were behaving entirely like a classical EM wave, its power would be proportional to intensity, but independent of frequency. Mechanical wave energy proportional to amplitude and frequency. Electromagnetic wave energy proportional to amplitude, intensity only. Would expect intense light of any frequency to generate photoelectrons, and also time delay for photo emission due to light of low intensity. This is the detailed results of the photoelectric effect. Overhead view with the electric field will or reverse battery polarity reverse to impede flow photoelectrons from the cathode to anode, and this is the graphical or the characteristic of a VI characteristic, current proportional to light intensity, stopping potential to light frequency. Uh, a modern medical practice is almost relying on the diagnosis and monitoring and observing the human health, which give the accuracy and precision, and plays an aid to treat out the situations in a very fast and in a secure way. For better times and at times of for worse, electronic has shaped our lives. Our living standards have improved, but we are also at the peril of deadly weapons that would not have appeared without the progress in electronics. So now, energy bands in solids. The allowable discrete values of n show that all energies are not permitted for the electrons. The electrons can have only certain discrete energies corresponding to the different integral values of n. In other words, electron energy is quantized. The allowable energies are represented by horizontal lines in a diagram called the energy level diagram of the atom. So this is the pictorial representation of any element or solids which is divided or which is classified into different subshells or bands, as we had studied the classification of metals or atoms or elements, and we come to the conclusion that by the Rutherford model in the atomic theory of that the atoms are or the elements are classified on the basis of combination of neutrons, protons, and the number of electrons present in that. And we had conclude to the theory that Electrons and protons are concentrated to the center of the atom or element, and that is known as the nucleus of an element. And the electrons are revolving around the orbits, are revolving around the nucleus in a particular orbit, depending upon the electronic configuration. And on the basis of a distribution of electrons, we had divided the electrons in the subshells 1s, 2s, 2p, 3s, 3p, 3, 4s, 3d, 4p. That is the designation of the different orbits. And the subshell carry the, if S is stand, then it carries 2 electrons in that orbit, and P stand for 6 electrons, and D stand for 10 electrons. And the electronic configuration of each element or atom is described on the basis of the atomic number. So we had a detailed knowledge about the electronic configuration and atomic number, and the energy bands in the solids are categorized on the basis of these configuration. Energy bands in crystal. A crystal is a solid consisting of regular and repetitive arrangements of atoms or molecules. Strictly speaking, ions in the space, if the position of the atoms in crystal are represented by points called lattice points, we get a crystal lattice. The distance between the atoms in crystal is fixed and is termed the lattice constant of the crystal. To discuss the behavior of electrons in crystal, we consider an isolated atom of the crystal. If Z is the atomic number, the atomic nucleus has positive charge Ze. At a distance r from the nucleus, the electrostatic potential due to the nuclear charge is in SI units. Band theory of solids. In an atom, the electrons in inner shells are tightly bound to the nucleus, while the electrons in outermost shell, that is the valence electrons, are loosely bound to the nucleus, because as the orbit which are far away from the nucleus or the distance is varying, so the orbit which is very close to the nucleus, the electrons travel in that orbit are very tightly bounded because they are attracted towards the nucleus with a more attractive force, while the orbits which are very far in, and in that the electrons are moving or around. So due to the distance, the force of attraction is little bit less, and they are valence electrons and loosely bound to the nucleus. During the formation of solid, a large number of atoms are brought very close together. The energy levels of these valence electrons are affected most. So the energy levels of these electrons, valence electrons, are affected most because valence electrons or valence band are the in that the atoms are or the electrons are to be taking part in various activities or various phenomena of reaction. The energies of inertial electrons are not affected much. The band formed by the series of energy levels containing the valence electron is called valence band. It is the highest occupied energy band. So on the basis of energy band diagram, or on the basis of energy band, we characterize the electrons or their shells or their electronic configuration uh, in the basis of energy band. That is, one who are very close to the nucleus, they are almost present in the conduction band, and those who are very far away from the nucleus, they are present in the valence band. It may be completely filled or partly filled with electrons. The next higher permitted energy band is called conduction band. It may also be defined as the lowest unfilled permitted energy band. It may be empty or partially filled with electrons. The electrons can move freely in the conduction band, and hence the electrons in conduction band are called conduction electrons. So whatever the electrons take part in the conduction or any activity or any activital phenomena are known as conduction electrons, and the electrons present in that band is known as conduction band. The energy gap between the valence band and conduction band is called forbidden energy gap or forbidden band. So there is a difference between the bands, both the valence band and the conduction band, and that difference or that empty space is known as forbidden energy gap or forbidden band. This band is formed by a series of non-permitted energy levels above the top of valence band and below the bottom of the conduction band. This band is formed by a series of non-permitted energy levels above the top of valence band and below the bottom of the conduction band. It is denoted by Eg and is amount of energy to be supplied to electron in valence band to get excited into the conduction band. When an electron gains sufficient energy, it is ejected from the valence band. Because of this, a covalent bond is broken and a vacancy for electron called hole is generated. So hole is nothing, it is a vacancy or the empty space created by moving a electron in sharing or in combining a covalent bond or participating in any other phenomena. So hole is nothing, hole is just a vacancy. It is supposed to behave as positive charge. Yes, the vacancy which is created is supposed to be a positive charge. This hole can travel to the adjacent atom by acquiring an electron from an atom. So this hole can travel to the adjacent atom by acquiring an electron from an atom. So this vacancy need to be filled up. So we can say that the electron is either moving to fill that vacancy, or we can say that the phenomena takes place and appears to be or assumes to be like that hole is moving. When electron is captured by a hole, the covalent bond is again re-established. The conduction of electrons are found in and above freely in conduction band. The hole exists in and move in the valence band. Distinction between metal, insulators and semiconductor. So, difference between metal, insulators and semiconductor. We had discussed about the metals, insulators and semiconductor, and metals, insulators and semiconductor are characterized on the basis of energy band diagram, and that is the most important base to differentiate the metal, insulators and semiconductor. There are many energy bands in solid as there are energy levels in parent atom. The electrical conduction properties of solids are concerned. Only the valence band and conduction band energies of the electron are considered. Completely filled bands and completely empty bands do not contribute to electrical conduction. So, by the means of this statement, we can say that any completely filled bands, that is, their orbital or their electronic configuration is almost complete, they are not going to participate in electrical condition because they are not having a free electrons, and we had already discussed that free electrons or the valence electrons plays a vital role in the electrical conduction. And if empty bands are there, that means there are no short of electrons present over there. So the empty bands do not contribute to the electrical conduction, obviously. When the electron is not there, then how the electrons are going to be moved or to take part in electrical conduction? The electron in the innermost filled shell do not take part in conduction process. Again, the innermost shell electrons do not take part because they are tightly or mostly attracted by the nucleus, and the attraction force is so high that they cannot take participation in conduction process. So we conclude that in conduction process, the valence electrons or free electrons are to be contributed. Next, the electrons in conduction band are free and move easily under an electric field. The electrons in valence band are attached to the lattice and are not free to move. If they acquire sufficient energy to cross the forbidden energy gap, they occupy the conduction band and states are available for conduction. So a minimum amount of energy is there, and if that amount of energy is acquired or gained by an electron which is externally provided, then and then only conduction of electron takes place. Okay, prior to that forbidden energy gap, they remain in their own still position. They are not going to participate without acquiring the energy. On the basis of band theory, solids are classified into three categories, which we had already seen, that insulators, semiconductors, and conductors are differentiate on the basis of band theory. And just a small review once again to give the classification of insulator through the some pictorial representation. Insulators are those materials in which the valence electrons are bound very tightly to their parent atoms. Hence, very large electric field is needed to remove them from attraction of nuclei. The band picture of insulator is shown in the figure. Valence bands and conduction band, and the gap between these two bands is denoted by Eg, known as forbidden energy gap, and the gap is very wider, as you've seen through the diagram. So a very high amount of energy is required to contribute the electron from valence band, or in conduction theory, to move the electron from valence band to the conduction band, because the energy or forbidden energy gap is very much high. So in their stable state, and this much of amount of energy is not possible to give to the insulators. If you just give the amount of energy to cross over the valence band electrons to the conduction band, and if you provide that amount of energy or greater amount of energy to the insulators, then the covalent bonding breaks down and electrons acquire the very high energy and do participation in conduction. But that much amount of energy taken by the electrons dissipated more heat, and that heat destroy the, or we can say that uh, burns out. So at the very high level of forbidden energy, the insulator get burns out. So, and that amount of energy is not possible to provide. Features of insulator: a full valence band, an empty conduction band, and band gap energy is of 5 to 10 electron volt. So this much of energy is to be required for moving a electron to take participation in conduction from valence band to the conduction band. very high resistivity of order of 109 ohm centimeter. Some samples at high temperature and under sufficient electric field, some electrons may move from valence band to conduction band. Hence, insulators show small conductivity at high temperature. Yes, the temperature plays a important parameter or important role uh, in contributing the conduction or phenomena of conduction of electron from valence band to the conduction band, because temperature is also a short of energy, and whenever the energy above the room temperature is provided, then their characteristic properties of the electrons or the atoms changes, and due to the changes in their characteristic properties, there is some sort of energy gained by the electrons, and they start moving from valence band to the conduction band. Now, semiconductors. A semiconductor material has electrical properties between those of insulators and conductors. So, semiconductor is the element which is lying between the insulator and conductor, and almost all properties which show in the insulator and which we are going to discuss in conductors, and the middle of those two, all the properties lying in the or plays a important characteristic in semiconductors. So semiconducting material has electrical properties between those of insulators and good conductors. The band diagram of semiconductor is shown. So in the figure shown to you, the conduction band and valence band is separated by a energy gap or forbidden energy gap, and by a amount of energy, but it is somewhat lesser than insulator. Features of semiconductors: almost empty conduction band and filled valence band with very narrow energy gap. That is, the energy gap is almost equal to 1 electron volt, and we had seen the energy gap or energy gap in insulators is between 5 to 10 electron volts. So the difference is very large. Okay, at 0 degree Kelvin, the valence band is 0 Kelvin, the valence band is completely filled and conduction band is empty. So at the temperature 0 Kelvin, we find the observation that valence band is completely filled and the conduction band is empty. But as the temperature increases, the electrons in valence band acquire enough energy to cross the small energy gap and move to the conduction band. Thus, the conductivity of semiconductor increases with temperature. So we can say the semiconductor in a semiconductor, the conductivity increases with temperature. Next, the electron moving to conduction band leave behind positive holes or created a vacancy in valence band. Hence, semiconductor current is the sum of electron and hole current flowing in opposite direction. The resistivity varies from 10 to 12 to 109 ohm centimeter. Example: germanium having energy gap is of 0.7 electron volt, and for silicon it is of 1.1 electron volt. Now conductors. The conductors have large number of free electrons available for electrical conduction. Conduction may be defined as solids characterized by a single energy band called conduction band, which is partially filled at any temperature. Alternatively, a conductor as a solid in which the conduction and valence bands overlap and there is no energy gap between the two bands. So, in the case of conductors, the conduction band and the valence band are overlap to each other, and at the room temperature, we can say that the conduction of electrons takes place, and a very small amount of energy is required to move a conductor or to move electrons in a uniform direction, and that contribute the electric current, because the electronic configuration of conductors or the conducting materials or the conducting elements are having the large number of free electrons. Their electronic configuration, by observing their electronic configuration, we will see that their free electrons are in very large quantity, and we know that for conduction or conduct electricity, electrons plays a vital role in electrical conduction, and free electrons plays a vital role in electrical conduction. So the conductors are having abundant amount of or a large number of free electrons, and due to that the conduction band and the valence band overlaps to each other. So this is the diagrammatic representation of conductor in which there is a zero energy gap or forbidden gap is zero, because conduction band and valence band overlaps to each other. As there is no forbidden gap, there is no structure to establish hole. The total current is simply due to the flow of electrons. Example: lithium, beryllium, sodium, and many more elements in the periodic table is characterized on the basis of electronic configuration as a conductors. Types of semiconductors. Now, after come to the difference between insulators, semiconductors, and conductors, semiconductors are of great importance in day-to-day electronics world. So, semiconductor is divided in two types of category. One is intrinsic semiconductor or pure semiconductor, and the other is extrinsic semiconductor or impure semiconductor. Here extrinsic or impure means that is you are adding some dopant, or impurity means the dopant, not the impurity like some wastage. You are adding some external elements to the pure element, then that category is considered to be the extrinsic semiconductors. It has been already discussed that semiconductor is a material whose electrical properties lie between those of insulators and conductors. A semiconductor has almost filled valence band and almost empty conduction band with a very small energy gap between the two. The semiconductors are of two types: pure or intrinsic. Second is doped or extrinsic or impure. And this extrinsic or doped semiconductor is further classified into two more categories. One is p-type semiconductor and second is n-type semiconductor. So as the research and uh, goes on continuous on the semiconductors, then through that research they conclude to the some devices formed by the semiconductors, and they play a vital role in electronic communication and electronic world. So semiconductors are the basis of electronic engineering, electronic applications, or electronic appliances. Next, pure or intrinsic semiconductors, semiconductor like germanium and silicon, has crystalline structure. As we observe the periodic table, the atoms are arranged in third group, fourth group, and fifth group are of crystalline structure, and the fourth group element has a purely crystalline structure. Their atoms are arranged in ordered array known as crystal lattice. These materials are tetravalent in nature or tetravalent in nature with 4 valence electrons in outermost shell. So the electronic configuration of fourth group element is having 4 valence electrons in their outermost shell. The neighboring atoms form covalent bond. The neighboring atoms form covalent bond by sharing 4 electrons with each other, so as achieved stable structure. A two-dimensional structure of germanium crystal lattice is shown in figure. So I'll show the lattice structure of a germanium. So this is the lattice structure of silicon. Just wait a minute. So germanium, instead of germanium, I'm showing the lattice structure of silicon. So all the silicon atoms in a crystal lattice or in the ordered form are arranged like this. Every silicon atom is bonded to its neighbor silicon atom. If I'm talking about the central silicon atom, it is having 4 valence electron in its outermost shell, and these 4 outermost electrons make a covalent bond with their adjacent silicon atoms. And if a small amount of energy is given to the intrinsic semiconductor, then as you observe through the figure that energy among all the 4 electrons or any electron get that energy and move to the conduction band and create the space over there, and it is noted with a vacancy name designated as vacancy, and this vacancy is generally known as hole. Next, in which the circle represents the atom core consisting of the nuclei and the inner 28 electrons. Each pair of line represent a covalent bond. The dot represent the valence electrons. The intrinsic semiconductor is the material in its very pure form. The band diagram of pure semiconductor is shown in figure. Sorry. Yes. Again, this is the pictorial representation of a semiconductor, pure semiconductor, in which valence band and conduction band and the central to these bands, at the very center position, one dotted line is marked, and this line is known as the Fermi level. So whatever the energy given to the semiconductor, if that sufficient amount of energy is taken by the valence electrons, then they cross the Fermi level and reach to the conduction band and plays a vital role in conduction of electricity, or electrical conduction takes place. So Fermi level is a criteria or a parameter defined to cross the barrier for playing a vital role in conduction of electrons. At zero temperature, all or 0 Kelvin temperature, all the electrons are paired and are contained in completely filled valence electrons. So by the above figure, we come to know that at 0 Kelvin, all the electrons are covalently bonded and contained in the completely filled valence band. No electron is free for conduction band. Hence, the conduction band is completely empty. The energy gap between the two bands is small. Example, the energy band gap between two bands is 0.72 electron volt for germanium. At 0 Kelvin, the energies of these magnitude are usually not acquired by the applied field. Hence, the valence band remains full, the conduction band empty, and material behave as insulator. At a room temperature nearly 300 Kelvin, some of the valence electrons acquire thermal energy greater than Eg, that is 0.72 for germanium, and hence they can jump to the higher conduction band. So the thermal energy provides the threshold or thrust to cross over the threshold, that is the Fermi level, and the electrons start jump from valence band to the conduction band. And in this way, by acquiring the sufficient amount of energy, electrons take participation in conduction. Next, they now act as free electrons and can move under the influence of a small applied field. The absence of electron in valence band is the hole under the influence of electric field. The electron from the neighboring covalent bond may fill this vacancy, that is, hole moves in a direction opposite to electron motion in valence band. The hole moves in the same direction as would a positive charge carrier. Hence, in semiconductors, there are two types of charge carrier. The total current is the sum of electrons and hole current. In intrinsic semiconductor, electrons and holes generated in pairs. Obviously, they are in pairs when electrons take participation in conduction. It left a vacancy over there, and that vacancy is known as hole. So, when any electron take participation in conduction, it creates a vacancy or a hole. So we can say that in intrinsic semiconductor, electrons and holes are generated in pairs. So law of mass action, according to the law of mass action, number of electrons into number of electrons and number of holes, number of electrons into number of holes is equals to Ni square. The law of mass action says that the conservation of law, according to the law of conservation. Next, at any given temperature, the number of electrons in conduction band and number of holes in valence band are same. With the rise in temperature, more and more electron hole pairs are formed and more charged carriers are available for conduction. Hence, the conductivity of intrinsic semiconductor increases with the rise in temperature. The intrinsic semiconductors have low conductivity. The most important, the intrinsic semiconductors have low conductivity because the participation of electrons, the valence electrons, are very few or very less. So the conductivity is very low. Doped or extrinsic semiconductor. So, thank you. This is all for the today's lecture, and I will continue this topic in the next lecture. And in further continuation of this topic, we are going to start with the new topic, that is superconductors, and the questionnaires and quizzes related to this topic. So, thank you all. Thanks a lot.